All right, in this next bit of reminder, we're going to remind ourselves about Bezout coefficients. And so at the start, we have two polynomials, f and g. F is t to the fourth plus 2t cubed plus 2t squared plus 2t plus 1. And g is t squared minus 1. We're working over q here. The first thing we're going to do is we're going to compute the GCD. So if you do long division, again, that's how do you compute the GCD? You use the Euclidean algorithm. How do you do the Euclidean algorithm? You do repeated long division. So you start off by dividing, in this case, the lower degree polynomial into the larger degree polynomial. And if I did it right, when you do the polynomial long division, which I'm not going to rehash here because you can do it, you should get that f is g times t squared plus 2t plus 3, and then the remainder is 4t plus 4. Great. So this is the first iteration of using the division algorithm. And if we want to label things, this is like our r-1 remainder. This is like our r0 remainder. And this is our r1 remainder. The next thing we're going to do is we're going to divide r1 into r0. So we're going to put a t squared minus 1 here. We're going to put an r1 here. And we're going to try to compute the quotient and the remainder. Now, 4t plus 4 is up to a multiple t plus 1. So we know that t squared minus 1 factors as t minus 1 times t plus 1. One of the t plus 1s is here. So that we must have a t minus 1, but we should probably also divide by 4. So it goes in evenly. Certainly this works. And then the remainder is 0. So this is our r2, and we found that the remainder is 0. And so what does that tell us? It tells us that the GCD, I'll highlight here in yellow, is the previous remainder. Let me use a color here. Great. So that's the GCD of these two polynomials. Now what? Well, if we solve for that remainder, what happens? And I'm going to put remainders because if you had to do more iterations of the division algorithm, there would be more remainders to solve for. If we solve for that remainder, what happens? We get that 4t plus 4 is, I'm going to move these terms here to the left at the cost of a negative sign. So we still are going to have our r-1, which is f. That's what this left-hand side was. But then we have to subtract off t squared plus 2t plus 3 times g. Or, to make it a little bit simpler, with the theorem I'm going to state, we have to add the negative of that times g. And to be even more silly, I'm going to put a 1 in front. All right. So if we solve for the remainders, what do we have? Well, on the left-hand side, we have a GCD. Usually we want our GCD to be monic, so we divide by 4 to make the leading coefficient 1. Let's not worry about that right now. And then we have a polynomial times f, and then we have plus another polynomial times g. That is, the GCD of these two polynomials is expressible as a polynomial combination of them. And that's the content of Bezout's identity for polynomial rings. So we're not gonna prove it, but you essentially run what's called the extended Euclidean algorithm, where you go back and you solve for remainders. It's covered in any ring theory course, any ring theory book. And it says the following. If you do this extended Euclidean algorithm, this is sometimes called Bezout's identity. Let me be clear here. So suppose f and g are non-zero polynomials, or at least not both zero polynomials, over K, and let D be the GCD of F and G. D again is a polynomial. Then what's the conclusion? Well, D is like the GCD here on the left, so there exists polynomials A and B over K such that D is AF plus BG. This is immensely helpful. It seems silly. It's not. It's immensely helpful. And Bezout's identity is something that's going to allow us to analyze quotients of polynomial rings that we're going to do in the following chapters. Okay, so Bezout's identity is very, very helpful, and it's the last of the reminder theorems from ring theory.